Hey, welcome back everyone. I'm going to do a quick help video for the online lab, which is graphing motion screencast. So if some of you are doing this and you want some extra help, like you're not quite sure how to take data or how to draw your three graphs that you're maybe being asked to draw, then I'm going to go ahead and show you how to do that. So let's go ahead and get to it. So first of all, you get to this point in the lab and I have a video where you're going to see the car as it travels. Actually, if I go back a little ways, this is in real time, and then I slow it down. And one of the first things you're going to do is start taking data. And so how do you take data? Well, you need position and you need time, right? We'll usually use like time first in that case, and this is going to be in seconds. So the very first data point I'm going to take, let's say that's going to be 0.12 seconds right there. And what is the position? Well, you're going to have to maybe zoom in on that while you watch the video. But from my viewpoint, I'm going to call that about 1.95 meters. I'm looking at like the front of the wheels. Notice there is some imprecision here, and there is some room for different answers. And that's why your data should not be exactly the same as your buddy's data, actually. So you can have position, we can call this X in meters if we want, or we could label this as position in meters over here. So notice I've got my first data point. Then I'm just going to play the video, play the screencast, and hit stop again. My second data point that I'm going to pick is going to be 0.55. That's a 5 seconds. So I've got my overlay of the timer on the left-hand side, and then I'm going to go ahead and do my best to come up with a value for the position at that point. All right, so if I was trying to be consistent, like pick the front of the car at every time and see how close I could get in terms of reading the meter sticks that are down there, maybe I would call this 1.78 meters. Maybe you disagree with that. It's okay. Just do your absolute best to be as precise as you can and you're going to be fine. Then you're going to continue doing that. Maybe you take 10 data points. Maybe you take 15 data points. Take a reasonable amount, like at least 10 data points. What's going to happen is your time is just going to increase as the whole thing continues, right? But let's think about what happens with your position. Your position is decreasing in value before the car hits the curb, right? This is going to go farther and farther down. You'll get to a point where it reaches 0. And then what's going to happen to the position after that? What would we expect to see? Well, we would expect to see that the numbers would increase. Maybe this is 0.2 and 0.4, 0.6, and so on. I'm just making up numbers. You get your own numbers from the data that you see on the video, but at this point, we would expect to see increasing numbers. So we would expect to see an increase in the position as measured from the 0 point, which is the curve. All right, and that's what we would expect to see. Now let's go ahead and talk about our graphs. Okay, so I'm going to go ahead and talk to you. What your first graph is going to be is a position versus time graph. So let's think about what you would expect to see for a position versus time graph. If you were the teacher and you were looking at a position versus time graph, what do you think this would look like? All right, well, hopefully you can come up with something like this. So you would have position, which would be X in meters right here. You would have time in seconds over here. And as time goes on, this is going to be your 0 mark for your position. As time goes on, we would expect to see something like this, all right, with our data, where the position changes with time and you end up with it'll bounce off the 0 mark and then it will continue to be changed in a positive sense. So that's what you would expect to see for a position time graph. So don't just copy that. You're going to actually have to use your own data to basically do this and then do a good job with figuring out what your graph scaling is going to be. Draw this in a legit way. I can put a link up in the upper right to how to scale graphs properly and figure out how to do this. All right, and next up, you're going to do 2 more graphs. So the first one is going to be speed versus time. So let's talk about speed, and the third graph you're going to draw is going to be velocity versus time. So let's talk about the difference between speed and velocity. Okay, so important things about the differences between speed and velocity. First of all, this is a scalar quantity and this is a vector quantity. So what does that mean? Well, this can only be positive, whereas a vector quantity can be positive or negative. All right, so an example of that would be is if I asked you how many steps have you taken today throughout your day. If you happen to wear one of those watches that tells you how many steps you've taken, that number would be a scalar amount. You either have taken a step or you have not taken a step. There's no direction associated with that. But if the question was, how many steps have you taken north today, or how many net steps have you taken in any direction, you could say, that would be more of a vector quantity or a vector question I would be asking about. So that would be like displacement would be the answer for that sort of second example, and distance traveled would be an example for the first one. So distance traveled is a scalar quantity, just like speed is, and displacement with a direction is a vector, just like velocity is. Now, they both use the same equation, basically. So it's going to be V average is going to be equal to delta x over delta t. Sometimes this is just written as t because it's understood that we start at t equals 0. Well, what does that mean? Well, we could say x final minus x initial divided by t final minus t initial. And that's what we're going to be using for this. So the very first one that I'm asking you to do is going to be a speed versus time graph. Now, how do we do a calculation? Well, we want to do a calculation before the collision, you could say. So you're going to pick 2 points. So pick 2 points before the collision. So you're going to pick 2 points before the collision. So I only have 2 points written in here. So this will be my initial position. And let me write another number down here. Let's say it's 1.4, something like that. All right. And that'll be my final position, let's say. I'm just going to pick those. You can pick any of these 2 points as long as it hasn't gotten to the 0 mark, because it's still decreasing in value. You can still pick any 2 points that you have and get a decent value for that. So let's just say this is 0.8. I'm just making up data at this point, but just for the example. All right, so we're going to say, well, what is then therefore our speed before the collision? So I could say speed before, and I'll label this as speed so we know what we're dealing with. So we're going to say it's x final minus x initial divided by time final minus time initial. Now, one more thing, we need to make this an absolute value because we're talking about this as a speed, so it cannot be negative. All right, if I'm going to use that data that I have over there, I'm going to go ahead and write this. Okay, so my final position is 1.4 meters. My initial position was 1.95 meters divided by my final time was 0.8 seconds. My initial time was going to be 0.12 seconds. So I do this, can put parentheses around here to suggest you're going to do the subtractions first, come up with those values, take the absolute value. That's going to be your speed before the collision. All right. Now, we also want to get the speed after the collision. So let me move this and we can talk about the speed after the collision. So it's going to be a similar calculation. So I will just say speed after. Oh, and I'll label it as speed as well right here. So we have the speed after the collision. Again, I'm just going to pick my initial point. Maybe I'll pick this one, and this is my final point over here. But we're going to do the same type of calculation. So we could say x final minus x initial divided by time final minus time initial. And we take the absolute value of that. So let's go ahead and think about after. This is after the collision. So after the collision, we've got, oh, I need to come up with some time values here. So let's call this, I don't know, 3.6. We could say 3.8, and this is 4.0 seconds. All right, so let's say that's our data that we have. Okay, so then we go back and we say our x final in terms of our position, it's going to be 0.6 meters. Our x initial was 0.2 meters. Our time final after the collision would be 4.0 seconds, and our time initial after the collision was 3.6 seconds. So you do this calculation, put in some parentheses here, and take the absolute value of that, and you've got your velocity after for speed. All right. Now we can do our two graphs relatively quickly. We can say, well, what would we expect? Well, we would expect in terms of a speed to have the same, roughly the same speed of the car before it collides with the curb as well as after. So if you think about it, remember the car is going just about the same speed as it heads towards the curb as it goes away from the curb, right? So you could say velocity in terms of speed, and so you would have some value, and then you have the collision. You might want to draw this slightly for like half a second or something like that, and then it will be about the same value over here. So it'll be at some positive speed value. In other words, it's going just as fast, more or less, backwards as it was going forward, so to speak, right? So that's kind of what we would expect. This part is optional. In other words, what exactly is happening during that crash in terms of the speed is going to be hard to represent, but you could represent that as that if you wanted to, or you could draw maybe dotted lines here and label it as a crash or something like that. All right, so that's going to be our graph for speed. What do you think the graph for velocity is going to look like? Okay, so remember, velocity can be negative. All right, so your velocity time graph should look something like this. It should have a negative value to begin with, right? Because before it, so we need to make it negative by putting a 0 right here before the collision. Then you have a quick change, a quick transition, and then you have a positive value. Whatever this magnitude is down below, like let's say this is just going to make it up. Let's say it's -1 meter per second, even though it was nowhere near that fast, then this should be about the same, +1 meter per second, because it's the same speed. It's just going to be in a positive direction. So up here is positive, down here is negative, if this is going to be our 0 point. So that's what we would expect to see. So this is our transition during the crash. So that's our transition during the crash. We would expect to have a line that connects the two, so to speak. But it's hard to get data as to exactly what's happening during that crash, but we would expect to see something like that. All right, so hopefully this has been helpful. I do want everyone to be up to speed and learn how to apply these ideas of position, speed, and velocity as we move in this unit. So if you have any comments down below, let me know, but I hope you all have a great day. Take care.